In the previous lecture, we have first of all discussed the criteria for the for application of classical statistics or the validity of statistical statistics. Okay, and after that, in the second lecture, you have seen the Maxwell-Boltzmann distribution law. In fact, after knowing Maxwell-Boltzmann distribution law, which is actually a law of classical statistics, now we can discuss a very important concept, which is the concept of density of states. And as an application of this concept of density of states, we can calculate the molar specific heat capacity of a perfect gas. So aim of this lecture is to deal with two important facts. First of all, we will know about the density of states. When you say density of states, it means density of quantum states. Okay. And after that, we will calculate the energy of a perfect gas, and calculating energy of a perfect gas, we will be able to find the molar specific heat capacity of a perfect gas. Okay, this is just an application of this concept. And as you have learnt in the previous lecture, that we can take a perfect gas or a dilute gas at high temperature as a classical system for which classical statistics can be applied, because you have learnt that in this condition the distinguishability of particle is valid. It means the wave packets of the particles or the molecules of the gas do not overlap, and we can say that the molecules of a perfect gas are identical but distinguishable. So the classical statistics can be applied. Okay. So we consider for our discussion a system of perfect gas, and this gas actually consists of n number of molecules, and it is in thermal equilibrium at temperature T. Okay. As you are considering a system of perfect gas, and you know the molecules of a perfect gas do not interact one another, and they obey the Maxwell-Boltzmann distribution law. Okay. Although in the derivation of Maxwell-Boltzmann distribution law, or the expression for the Maxwell-Boltzmann distribution function, first of all we have considered discrete energy levels. Okay. But as you know that in a classical system the energy levels are almost continuous, so we will consider here that the energy eigenvalues of this system of perfect gas is not discrete but continuous. Okay. Now we will define the two important terms which actually we have to find. So first of all, the term which is to be defined is occupation probability or the distribution function. Actually, you have learnt in very detail about this occupation probability and distribution function in the previous lecture. This is actually called Maxwell-Boltzmann distribution law 2. Actually, you have learnt that the average number of particles or molecules per quantum state or per phase cell is actually called the occupation probability or the distribution function. So what is occupation probability or distribution function? It is simply the number of particles per quantum state. Okay. In a quantum state or in a phase cell, what is the number of particles or molecules? That represents actually the occupation probability. Okay. And in the previous lecture, you have already obtained the expression for the occupation probability or distribution function, and you have seen that at energy E, the occupation probability or the distribution function denoted by this symbol f of E is equal to e to the power alpha times e to the power beta E, where alpha and beta are actually Lagrange indeterminate multiplier. And we have denoted this e to the power alpha by the symbol A, and you know beta is equal to minus 1 by kt. So you can write this Fe equal to A times e to the power minus e by kt. Actually e to the power minus e by kt, this is called Boltzmann factor. So this is the expression for the occupation probability or the distribution function, which actually represents the average number of particle per quantum state or per phase cell. Mark it. Now, what is this density of states? Actually, you know that energy distribution here is continuous. So we will talk about a particular range of energy, although that range may be very small. Actually, this density of states is defined as the number of quantum states in a particular energy range. So if you denote this density of states by the symbol G of E dE, it means what? It means this is simply the number of quantum states for the energy between E and E plus dE. It means if energy of the system lies between E and E plus dE, then what is the number of quantum states in this energy range? The number of quantum states in the energy range between E and E plus dE is simply called density of states. Okay. So now after knowing the occupation probability of distribution function and the density of states, you can say what will be the number of molecules whose energy lies between E and E plus dE. As you know that in one quantum state, the number of particle, P for particle is what? This is equal to F of E. Just we have defined. Average number of particle in one quantum state is equal to the distribution function or occupation probability. So you can say that in one quantum state, the number of particle present is equal to F of E. And as G of E dE, this represents the number of quantum states for energy between E and E plus dE. So the number of quantum in this number of quantum state, that is GED, what will be the number of particle? That will be simply F of E times this G of E dE. Okay. In one quantum state, the number of particle is Fe. So in GE quantum state, the number of particle will be Fe into GE. Actually, this dE is multiplied here to indicate that this energy is not strictly equal to E, but it lies between E and E plus dE. Okay, so I think we have understand that the number of molecules or number of particles with energy E and E plus dE will be equal to what? If it is denoted by the symbol N of E dE, then that will be equal to G of E dE times F of E. Okay. Now we will try to find first of all this G of E dE, which is called density of states. Okay. And after F of E is already known here from Maxwell-Boltzmann distribution law. So when we will calculate the value of G of E dE, which is called density of states, then by the use of this equation A2, we will be able to find the number of molecules of this gas having energy between E and E plus dE. So let us try to find this density of states G of E dE first of all. And for this, as you know, our system is a system of perfect gas, and the molecules of a perfect gas are non-interacting. And as I have discussed in the previous lecture too, that since the molecules are non-interacting, so these molecules will have no potential energy. And so energy of this molecule means simply its kinetic energy, and that is simply its translational kinetic energy. Okay. So you can say that the energy, which is actually translational kinetic energy of a molecule, E, will be equal to what? That is P square over 2m. Actually here, what is this P? P is the linear momentum of the molecule. This is linear momentum, you know. This is a famous relation, okay? And from this, we can find if P equal to a square root of 2me, okay? Now, as you can see that this energy is related to the momentum of the particle. So you can say that when energy of the molecule is E, its momentum is P, okay? And when its energy is E plus dE, you can say that the momentum of the molecule is P plus dP. So saying that energy lies between E and E plus dE, and when you say that momentum lies between P and P plus dP, both are same statement. Okay. So if you say that this N of E dE represents the number of molecules having energy between E and E plus dE, that number will be simply equal to the number of molecules having momentum between P and P plus dP. And you can also denote that by the symbol N of P dP. Both will be actually same. So for this, first of all, we will find the density of states in terms of momentum, and then by the use of this relation, we can find the density of states in terms of energy. And for this, we will need to know the value of dP in terms of E, because you can see that here P is already defined in terms of E, but we will have to know what will be the value of dP in terms of this E. For this, let us take the differential of this equation as P equal to a square root of 2me. So what will be dP? You can easily find. Since this 2m is a constant factor, so let us take 2m to the power half outside of the differential operator, and we will take the differential of e to the power half. What will be the differential of e to the power half? That will be 1 by 2 e to the power minus half, and that can be written as 1 over e to the power half times dE. Okay. Now you can see this 2 under a square root and this 2 which is not under a square root, 1 will cancel, and your result will be what? This is m by 2e to the power half times dE. So this result actually relates dP with dE. dP with dE. Now, as you know that our aim is to find the number of quantum states between energy E and E plus dE, or the number of quantum states between momentum P and P plus dP. And you have learned in the previous lectures that H cube is the volume associated with one quantum state. It means volume in phase space associated with one quantum state or one phase cell is equal to H cube. Okay. So if we will calculate the volume in phase space for the energy between E and E plus dE, or for the momentum between P and P plus dP, then we can find what will be the number of quantum states in that volume. Only then we can find. And so first of all we have to find the volume in phase space for the energy lying between E and E plus dE. Or you can also say we will have to find the volume in phase space corresponding to the momentum between P and P plus dP. And as you know, the volume in phase space delta gamma, you have learnt in the previous lecture that this volume is also called hypervolume, and this is actually equal to the volume in configuration space or position space times volume in momentum space. Okay, so you can say that this delta gamma, which is volume in phase space corresponding to the momentum between P and P plus dP, that will be equal to volume in position space. And volume in position space is given by this integral, in triple integral of dx dy dz. This is actually the volume in position space times the volume in momentum space. Volume in momentum space is given by triple integral of dpx dpy dpz. Actually, this product gives the volume in phase space for momentum between P and P plus dP. Actually, I have written here x, y, z, px, py, pz, but when actual problem will be solved, there should be the proper limits. So delta gamma, which represents the volume in phase space for momentum between P and P plus dP, or you can say for energy between E and E plus dE, is equal to this much, which I have defined in this equation 1. But you know, the volume in position space, which is this triple integral of dx dy dz, this is nothing. This is simply the volume of the container in which our system is contained. It means if you have considered a container of volume V in which your perfect gas is enclosed, then this integral simply represents that geometrical volume V, which is actually the volume of this vessel or this container. Okay. Now, what is this volume in momentum space? That is triple integral of dpx, dpy, dpz. What is this? Actually, this is nothing. This is simply the volume in momentum space contained between two concentric spherical cells of radii P and P plus dP. P and P plus dP. So this region which I am just shaded here, actually this volume represents the volume of this shaded region in momentum space. And what will be this volume? You can see if you write the volume of this sphere of radius P, if this volume is tau, then this will be what? This is 4 by 3 pi P cube. P is the radius in momentum space. And so the volume of this shaded region, this is simply the slight increment of the volume of a sphere of radius P. Or you can say this is simply the differential change in the volume of the sphere of radius P. So what will be that volume? If that volume is d tau, then that will be differential of 4 by 3 pi p cube. Differential of 4 by 3 pi p cube. And 4 by 3 pi is a constant factor. And differential of p cube, this will be what? This is 3p square dp. And this 3 and this 3 will cancel out. So your result is what? Your result is 4 pi p square dp. So you can say that the volume in momentum space for the momentum lying between P and P plus dP is simply equal to 4 pi p square dp. Okay. So you have calculated this triple integral of dx dy dz, which is simply equal to volume of the container, and this volume in momentum space, which is 4 pi p square dp. Okay. Now let us substitute these two values in this equation 1. So you can say what will be the volume in phase space corresponding to the momentum between p and p plus dp. That will be v times this 4 pi p square dp. So I have written it here. You can see that the volume in phase space corresponding to the momentum between p and p plus dp, or energy between E and E plus dE, this delta gamma will be v into 4 pi p square dp, or you may write it 4 pi v p square dp. Okay. But as I have told you earlier that in h cube volume, where h is Planck's constant, there is one quantum state. In h cube volume, what is the number of quantum state? One quantum state. You have learned previously. So in unit volume in phase space, the number of quantum states will be 1 by h cube. So in this delta gamma volume in phase space, what will be the number of quantum state? Number of quantum state will be delta gamma divided by h cube. Divided by h cube. So you can see I have written this number of quantum state for momentum between p and p plus dp by the symbol g of p dp. Actually this g of p dp represents the number of quantum states in phase space between momentum p and p plus dp, and that will be equal to what? That will be delta gamma by h cube. But delta gamma is what? Delta gamma is 4 pi v p square dp. So this will be equal to 4 pi v p square dp divided by h cube. I think we have clearly understand. Okay. Now when you will change the parameter p into e, then this same number g of p dp will be represented by g of e de. Both are same. For this, if you want to write g of e de at the place of g of p dp, you have only to change p and dp in terms of e. Okay. So g of e de is equal to 4 pi v by h cube, and this p square, you know p square is equal to 2me, and this dp you have calculated earlier that this dp is equal to m over 2e to the power half de. Okay. Now after simplification, here this root 2 will cancel out, and here there will be root 2. So and 1 2 will be taken from this 4. Then in a simple form you can write this expression like this: g of e de equal to 2 pi v by h cube times 2m to the power 3 by 2 times e to the power half de. Okay. And this expression can be written like this: g of e de equal to c into e to the power half de, where c has been written at the place of this much, 2 pi v over h cube 2m to the power 3 by 2. So you can see this is the expression for the density of states, that is the number of quantum states in the energy range between E and E plus dE. And you can see that this density of states is just directly proportional to a square root of energy E. Okay. So I think we have understand this calculation. The calculation is very easy. Okay. Now after knowing the expression for the density of states, that is the number of quantum states lying between energy E and E plus dE, now we can easily find the number of molecules in this energy range. Okay. As you have learnt earlier that the number of molecules with energy between E and E plus dE is denoted by the symbol N of E dE, and that is equal to G of E dE F of E. You have just learnt it. See here. I have already explained how this expression has been written. This is your N of E dE equal to this much. And you have already calculated the value of G of E dE and F of E. This is occupation probability or Maxwell-Boltzmann distribution function. You can put the values of these two quantities and then you will get the expression for N of E dE. As you have calculated here that this G of E dE is equal to C times E to the power half dE, and this distribution function F of E is equal to A E to the power minus E by kt. Okay. So this N of E dE you can see will be equal to what? This is simply Ca times E to the power half E to the power minus E by kt dE. Okay. Now, if you want to find the total number of molecules which actually has been assumed N in this system, how you can find that? This number N of E represents the number of molecules having energy lying between E and E plus dE. And as this is a classical system, and in classical system you know the kinetic energy may lie between 0 to infinity. Why? The least value of kinetic energy in classical physics will be 0 and the highest value will be infinity. Because in classical mechanics there is no restriction on velocity. Velocity may be infinity in classical mechanics. Although in relativistic mechanics it is limited, it cannot be greater than c. But in classical physics you know there is no restriction on the upper limit of speed. So the energy lies between 0 to infinity. So when we will integrate this N of E dE between the limits 0 and infinity, we will simply get the total number of molecules in this system. And as we have assumed that the total number of molecules is equal to N, so this N will be equal to integral from 0 to infinity N of E dE. Okay. Now let us substitute the value of N of E dE here. You have seen that this is equal to Ca, since Ca is constant, so it has been taken outside of the integral, times E to the power half E to the power minus E by kt dE. Now let us try to evaluate this integral, and for evaluating this integral let us consider that this E is equal to epsilon into kt. Actually epsilon is here just a number, okay, because kt has already the units of energy, okay. And so dE will be what? This will be kt times d epsilon. Okay. Now instead of E in this expression we will substitute epsilon kt, and at the place of dE we will put kt times d epsilon. And what will be the limits? You can see here in equation 4 this 0 is the lower limit of E. So when E is equal to 0, you can see from here this epsilon will be also equal to 0. So the lower limit will remain same. And when E is equal to infinity, the upper limit, see here, then from this expression you can see that epsilon will be also infinity. So the limits remain same. Okay. When you will change the parameter, limit will not change. So you can write N equal to Ca times integral 0 to infinity E to the power half, but E is epsilon kt. So epsilon kt to the power half. So I have written here kt to the power half times epsilon to the power half, and times E to the power minus E by kt. You can see E by kt is equal to simply epsilon. So this will be E to the power minus epsilon, And at the place of dE, we will write here, you can see kT times d epsilon. Okay. So this kT to the power half times kT, this will be kT to the power 3 by 2, and it can be taken outside of the integral. So this is Ca times kT to the power 3 by 2, and integral from 0 to infinity epsilon to the power half, you can see, and times e to the power minus epsilon d epsilon. Actually, this is just a standard integral which can be evaluated in terms of gamma function. I hope you have an idea of gamma function. Actually, value of this integral is simply root over pi by 2, or you can say that this is simply 1 by 2 times pi to the power half. Okay. So let us substitute this value of integral here, and you can see n will be equal to, sorry, the page has been turned, but this will be okay, don't worry. This is just a regular drawback of my iPad. So you can see n equal to Ca kT to the power 3 by 2 times root over pi by 2. Okay. And so from here you can calculate the value of product of these two constants Ca, and this will be equal to 2n over pi to the power half times kT to the power 3 by 2. So in this way we have obtained the value of this Ca. Now let us substitute the value of this Ca in this expression. I have actually repeated this expression. You have seen earlier that n of E dE is equal to Ca times e to the power half times e to the power minus e by kT dE. Now instead of this Ca, you can write this much. Okay. So n of E dE is equal to 2n over pi to the power half kT to the power 3 by 2 times e to the power half times exponential to the power minus e by kT dE. So this is the expression for the number of molecules of this perfect gas whose energy lies between E and E plus D. Okay. Now after knowing this number of molecules, we can easily find the energy of this gaseous system in thermal equilibrium at temperature T. And when you will calculate the energy, then you will be able to find what will be the molar specific heat capacity. So now first of all let us try to find the energy of this system. Okay. As you know, if your aim is to find the molar heat capacity of this gas, you know, if U is the total energy of this gaseous system and the number of moles in this gaseous system is mu at temperature T, then from the definition you know that molar heat capacity Cv is defined like this. This is 1 over mu du by dt. This is just the basic definition. Okay. If you take that mu is equal to 1, then you know Cv is simply defined as du by dt. du by dt. So from this definition it is clear that if our aim is to find Cv, we have first of all to find what will be the energy U of this system. As you know that this E is the energy of this molecule. N of E is the number of molecules whose energy lies between E and E plus dE. As dE is very small, so we can take that the energy of all these N of E molecules is almost equal to E. So as each molecule has energy E, okay, and Ne is the number of molecules, so what will be the total energy of this Ne molecules? This will be E into Ne. Are you getting the things or not? since energy of each molecule in Ne is equal to E and number is Ne. So the total energy of Ne molecule will be E into Ne. And when you will integrate this result for the entire range of energy, you will get the total energy. So you can write the total energy U of this system is equal to integral 0 to infinity E into N of E dE. Okay. Now N of E you have obtained already here. You can see this equation 5 gives the value of N of E. Okay. And put this value here and multiply that result by E, since the expression for N of E dE contains E to the power half, and when you will multiply by this E, the result will be simply E to the power 3 by 2. And all the constant factors independent from this energy E has been taken outside of the integral. So U is equal to 2n over pi to the power half kt to the power 3 by 2 integral 0 to infinity e to the power 3 by 2 times e to the power minus e by kt dE. Again this integral will be evaluated by the same method of substitution. We will take E equal to epsilon kt. Okay. And dE will be equal to kt times d epsilon. And as you have seen earlier that limits will not change, limit will remain same. So replace this E by epsilon kt, and when E is equal to epsilon kt, then you can see that E divided by kt from here you can see will be simply equal to epsilon. So let us substitute all these things here. You can see I have written E equal to this much, dE is equal to this much, and so U will be what? This is 2n over pi to the power half kt to the power 3 by 2, and at the place of E to the power 3 by 2 I have written here kt to the power 3 by 2 times epsilon to the power 3 by 2 and e to the power minus e by kt, but e by kt is equal to epsilon, and at the place of dE we have written kt times d epsilon. Okay. Now kt to the power 3 by 2, this and this will cancel out, only this kt will remain, this kt. Okay. So this is 2n over pi to the power half times kt and integral epsilon to the power 3 by 2 into e to the power minus epsilon d epsilon. Again from the concept of gamma function you can write the value of this integral is 3 by 4 root pi. That was 1 by 2 root pi, this is 3 by 4 root pi. So U is equal to 2n kt over pi to the power half times 3 by 4 pi to the power. So now this pi to the power half will cancel out, and this 2 will cancel by this, and so your energy expression is U equal to 3 by 2 n kt. And you know this is the well-known formula or well-known result for the energy of a perfect gas. You have definitely studied these things in your lower classes in kinetic theory of gases. Okay. Here N is the total number of molecules present in this gas, K is Boltzmann constant, and T is temperature. Now as you have considered that the number of moles in this gaseous system is mu. Okay. And you know that in 1 mole the number of molecules is equal to Avogadro number. In 1 mole number of molecule is what? That is equal to Na. Na is Avogadro number. So in mu moles what will be the number of molecules? This will be mu into Na. But we have considered earlier that the total number of molecules is N. So the total number of molecules N will be simply equal to mu Na, where mu is the number of moles and Na is Avogadro number. So at the place of n in this equation 7, you can write mu into Na, where mu is number of moles and Na is Avogadro number. So replace that n by mu Na. So you can see U is equal to 3 by 2 mu into Na times K into T. Okay. But you know that Na and K both are universal constant, and the product of Na and K is equal to R, which is called universal gas constant. So instead of Na times K, we have written here R. So the energy of this perfect gas at temperature T is equal to U equal to 3 by 2 mu RT. So if you have to say what is the energy of 1 mole, the energy of 1 mole will be simply equal to 3 by 2 RT. And energy of mu moles is 3 by 2 mu RT. Now, after knowing the expression for energy of this perfect gas, which is also the well-known result, because this result definitely you have studied in your lower classes in kinetic theory of gases. Now you can easily find the molar specific heat capacity of this gas. As you know, the molar specific heat capacity denoted by the symbol Cv is defined by 1 over mu du by dt. And here you can see this mu, and when you will substitute the value of u, you can put the value, this is 1 over mu, and here 3 by 2 mu r is constant, so it will be outside of the integral differential, and this is dt by dt. Here this mu and this mu will cancel out, dt is equal to 1. So Cv is simply equal to 3 by 2R. So molar specific heat capacity of a perfect gas is equal to 3 by 2R. And you can see this result in your in kinetic theory of gases, or you can say in equipartition of energy. I have already discussed in the heat and thermodynamics playlist of my channel this fact, and this result agrees with that. Actually, this result simply says that the molar heat capacity of a monatomic gas is equal to this much. So you can say that as this value of Cv is same as that of a monatomic gas, so the perfect gas just behaves as a monatomic gas. Okay. So I have mentioned it here. You can see this is the molar heat capacity of a monatomic gas having 3 degrees of freedom due to translational motion. So in our discussion, we can always treat the perfect gas as a monatomic gas. So I hope you have understand. This was a very simple calculation, simple concept, but very important. Okay. So after these 3 lectures on Maxwell-Boltzmann statistics, so many facts have been clear to you, but the chapter is not finished here, but we will learn something more in this classical statistics in the forthcoming lectures.